Synchronous Fireflies. If you walk along the bank of Thailand's Mekong River at night, you might witness one of the most incredible visual displays in nature, tens of thousands of fireflies blinking in perfect unison. Nobody knows why they do it, just that it's part of their mating ritual. But the real mystery is how they are able to synchronize their pulsing lights. It's a localized communication that spreads through the swarm like ripples in a pond. If you were to watch the light show from the beginning, you'd see it start with just a handful of fireflies who found the right rhythm. From that small pocket, the rhythm sweeps through the rest of the population until they're all perfectly synchronized. What was chaos becomes machine-like precision. It's not just Thai fireflies that do it, either. The same phenomenon has been seen everywhere from Japan to Texas. All we know is that it's a male-exclusive behavior. Processionary caterpillars. The pine processionary is a little brown moth that lives in pine forests throughout Europe and Asia. Despite its size, it's one of the most destructive pests in the world. Its caterpillars can destroy up to 73% of a pine forest in a single generation, decimating it beyond hope of recovery. The caterpillars start life in basketball-sized sacs strung up at the tops of pine trees. Even though they're only about 20 millimeters, 78 in, long at birth, their mandibles are already strong enough to slice through tough pine needles. At first they only eat the needles contained in their communal cocoons, but once they grow large enough, they emerge in the bizarre fashion that led to their name. They form a perfectly straight train that can contain hundreds of individual caterpillars marching head to tail. This procession marches across their home tree. When it's been consumed, they take to the ground and start on a new tree. Every night they go out, and at dawn they return to their treetop cocoons, to sleep and wait out the day until they can feed again. Trap building. Olimerus decimarticulatus is a species of ant that lives in the Amazon jungle. While most ants are foragers, picking up food wherever they can find it, the Olimerus genus lets their prey come to them. They build traps in the stems and leaves of trees, then lie in wait. When an insect stumbles over one of the trap doors, the ant lunges out and snatches one of its legs. It then wedges itself in place, allowing it to hold on to prey larger than 13,000 times its size. At the same time, it sends out a pheromone signal to the other ants, and that's when things get vicious. More ants will grab the insect's other legs and pull them apart, forcing it into a spread eagle position on the leaf, so that it can struggle while it's being dismembered. As if that wasn't cruel enough, Olimerus ants rig their setup so that there's practically no escape. They'll station up to 40 ants in traps on a single leaf, turning it into a biological minefield. The trap doors themselves are built out of the tree's natural fibers, so the final trap just looks like something that grew on the tree naturally. Fungus grooming. Agriculture is one of the things that humans can safely claim as their own. At least, that's what we thought until the 1970s, when it was discovered that several species of leafcutter ants maintained mushroom farms. The fungus is cultivated in carefully managed gardens, and the ants have evolved to be extremely thorough caretakers. Leafcutter ants are best known for the way they slice off bits of leaf and carry them back to their colonies. But the leaves aren't food, they're fertilizer. The ants drop the fresh leaves into the thinnest sections of the garden to boost growth in those areas. Then, they chew off weaker fungus growths, holding on to several enzymes that come from the fungus. When the ants poop the unprocessed enzymes back into the garden, they kickstart the decomposition of all the fresh leaves that just came in, fueling new fungus growth. But that's all just exposition for the truly bizarre part. Certain ants within the colony have the job of going around and licking all the fungi. By doing this, they are spreading a bacteria that kills a competing fungus, one that would destroy the whole crop if allowed to thrive. In other words, the ants are using a pesticide to maintain their farms. Electric navigation. The life of a flower is a non-stop, bloodthirsty competition. They've evolved dozens of signals to lure pollinators, like bees and butterflies, to visit them and spread their pollen. Every time a bee chooses one flower over another, it stands a chance of wiping out an entire genetic line. As it turns out, there's more to this than colors and scents. Bumblebees can actually sense the minute electrical field created by flowers, and use it to decide which flowers would have the best nectar. Flowers have a positive charge, which stands out like a beacon in the fog of charged particles that are always floating through the air. Each flower, however, has a slightly different charge. Bumblebees can learn to distinguish between different voltages, and they remember what a specific charge looked like if, for example, they really liked sipping on that flower's nectar. Even weirder, the flower's charge reacts when a bee lands on it. It surges, then dims again when the bee flies away. Like an occupied sign on a porta-john, the surge lets other bees know that it's currently being used. Troll nymph. On a recent expedition into the Suriname rainforest in South America, biologists discovered 60 species that had previously been unknown to science. One of these, possibly, was a tiny nymph with a lush head of iridescent, waxy hair. We say possibly because the team only managed to catch one incredible photo of the nymph before it hopped away and disappeared. Nymphs are young insects that often completely change as they grow into adulthood, so it's possible that this was just a young version of an insect we already know about. Nothing like it has ever been seen. The hairs are actually thin follicles made out of wax, which are probably used to trick predators into grabbing the wrong end. The hair grows on its butt. Like a lizard's tail, they can probably break away to give the nymph a chance to escape. But they have a dual purpose. When the nymph is threatened, it pops away like a flea, jumping to hundreds of times its body height. The hairs slow its fall like a parachute, allowing it to glide even farther. Which is cool, but it still doesn't change the fact that the whole thing looks like an 80s Roald doll. Ants use meth. According to Fermat's principle of least time, a light ray will move through a medium in the fastest possible path, but not necessarily the shortest. That's one of the reasons light refracts when it passes from air to water. And, surprisingly, ants follow the exact same law. When a colony of ants is presented with a food source, they form a train that gets them to it in the least amount of time. But that makes sense. Any animal would do the same. What's interesting, though, is that they will create a weaving path over varying terrains to create the most mathematically logical route. If they move more slowly over a certain terrain, for example, they'll skirt around it, traveling a farther distance, if it means sticking to smoother terrain. But they also won't hesitate to slice across the harder terrain if it would take too long to go around. Obviously, it's not a logical process. The ants aren't punching little calculators to figure this out. It's more of a microevolution of the ideal path. Every time an ant returns with food, it leaves a pheromone trail. With multiple pheromone trails to choose from, newcomers will take the quickest one, strengthening it with their own pheromones. Eventually, the dozens of initial trails coalesce into a single, mathematically efficient trail. Mormon cricket cannibalism. Shield-backed katydids, more commonly referred to as Mormon crickets, live in the southwest U.S. Every few years, population explosions lead to massive swarms that sweep across farms and towns and cities. Swarms can contain millions of individuals, and they're all looking for the same thing, protein. So the swarms start to move. They can't fly, but these little guys will crawl over 1.5 kilometers each day, carpeting the ground with their bodies. What keeps them on the move, however, is a strange dynamic. With such large swarms, only the katydids in the front get access to food. By the time the stragglers catch up, the food is all gone. Driven crazy with hunger, they attack the closest protein source, the katydids in front of them. Eventually, the katydids at the front of the swarm have eaten their fill, but they need to keep moving anyway to avoid being cannibalized by the increasingly hungry swarm at their back. This combination of hunger and fear propels them through one of the largest mass migrations in the country. Insect homosexuality. Mammals and birds are no strangers to homosexuality, as we've seen plenty of times. Less studied, however, is the proliferation of gay sex in the insect world. But while larger creatures often have deeper reasons for pursuing same-sex relationships, For insects, the motivations are less pure: confusion, manipulation, and sheer desperation. A lot of times, it's an accident. The majority of insects have evolved a mating process that's quick and dirty. With the constant threat of predation over their heads, they need to take care of business as quickly as possible. Guided mostly by pheromones, male insects are often confused by the lingering female scent on a male that's just had sex, and will pursue and mount him indiscriminately. In some species, internal damage from these confused encounters has actually prompted the evolution of female-like genitalia in males, just so they can avoid being punctured in the wrong place. And then you have malicious intent. Certain beetles will have sex with another male in the hopes that their sperm will make it into the next female he mates with. Ants that eat computers. In certain states in the southeast U.S., fire ants are being slaughtered. That's good news for most people, but their replacement might be even worse. In 2002, a species of invasive ant was discovered by an exterminator in Texas. Dubbed crazy ants, they were killing all the fire ants in sight. But crazy ants are becoming infamous because of the bizarre way they invade electronics, chew through the circuitry, and kill themselves when they reach the live electric wiring. But as they die in a puff of smoke, they send out a chemical that calls other ants to the electric source to avenge their death. The result is a swarm of ants attacking the wiring in computers, cell phones, and TVs. And they were spreading. What started in Texas quickly moved across Mississippi and Florida, and is now moving north through Georgia. Crazy ants have a knack for reproducing faster than native ant species, outcompeting them for food, killing everything that's left, and taking over their nests.